So
Okay.
thanks for coming back. Um, so I'm going to start out today with some simple things. Just the cumulative hierarchy, because this is going to be so important for what we do later, and it's relevant for motivating the other things I'll talk about. So it's just defined by iterating the power set transfinitely. So you start with nothing, and then you take the power set of nothing and the power set of that, and you iterate that through all of the transfinite ordinals. So at limit ordinals, you take unions, and then the universe of sets, or the pure sets, well-founded sets, is given by taking the union of all the levels of the cumulative hierarchy. So obviously V is a proper class. And I mean, the axioms of set theory imply that every set is in V. So in other words, every set belongs to some level of the cumulative hierarchy. And this is really equivalent over the other axioms to the axiom of foundation. Yeah, so in set theory, you're only typically interested in these kinds of sets, even though it seems like there are many sets in math that aren't of this form, like the set of natural numbers. But okay, everything is encoded into V, and so V is all we care about. So we basically added the axiom that V is the whole universe of sets into the axioms of set theory. And it's because anything you want to do in math, you can do staying within V. Okay. So set theory, you could see it as the study of V, but the issue is that basically every question you can ask about V is independent of the axioms. So the key example, of course, is the continuum hypothesis. So this is just the question of whether 2 to the aleph 0, the cardinality of the continuum, is equal to aleph 1, which you can see as a question about V omega plus 2. It's a first order question because you can ask, is there a well ordering of V omega plus 1? That would be an element of V omega plus 2, essentially, whose initial segments are countable. Or you could ask, I guess, is there a set A contained in V omega plus 1 that is uncountable? But not in bijection with V omega plus 1. Okay, so the continuum hypothesis is the question about V omega plus 2. So this is the negation of the continuum hypothesis here. This is the statement of the continuum hypothesis. So it's a simple first order statement. Both it and its negation can be stated in a very simple way over the structure. But the question can't be answered based on the axioms of set theory. So that's the Cohen Gödel theorem. So the continuum hypothesis is independent of CFC. And the continuum hypothesis is, I don't know, it's a very basic question at the bottom of the hierarchy, and it's pretty hard to say things about the omega plus 5 as well. So it's really the situation is that the simplest questions in the theory of uncountable sets just don't seem to have answers on the basis of CFC. So one idea that was proposed to solve these questions was to introduce large cardinal axioms. So this is really Gödel's program. By adding large cardinals to CFC, so inaccessible cardinals and malo cardinals, solve the problems that are unsolvable on the basis of the CFC axioms. So large cardinal axioms are supposed to be generalizations of the ZFC axioms. Gödel suggested that they were just, true on the basis of reflecting on what the axioms meant, so that you should just sort of think about it and see that there must be an inaccessible cardinal. Maybe that was, I don't know, a bit, well, that was how he felt, but it's a little hard to justify that, I don't know, philosophically. But anyway, if you try to do this, it's unfortunately the continuum hypothesis just can't be solved in this way. And neither can many of the questions that had been raised by the time the independence phenomenon was discovered. So sort of unfortunate negative end to this program, even though as I mentioned last time, large cardinals do solve many questions that are unsolvable in CFC. So for example, I mentioned the singular cardinals problem. So the generalized continuum hypothesis for singular cardinals follows above a strongly compact cardinal. And then there are all the determinacy hypotheses that follow from large cardinals that I discussed last time, which actually allowed large cardinals to solve, I don't know, hundreds of open problems that had been posed by descriptive set theorists in the 1930s. And that turned out to be independent of the original axioms. But as for the continuum hypothesis, that remained unsolvable from large cardinals. And really there's something like a proof that large cardinals can never solve the continuum problems. It's called the Levi-Solovay theorem. It shows that large cardinals of the form I was discussing last time, embedding principles, they just are sort of orthogonal to the value of the continuum. So another approach to answering or solving the continuum hypothesis is to sort of step back and consider structures that are less complicated than the full universe of sets. So one of these structures, the simplest, is the constructible universe. So this is defined by instead of iterating the power set operation in the definition of the cumulative hierarchy, you iterate a restricted version of the power set operation. So you let L alpha plus 1 be defined by recursion to be the set of all definable subsets of the structure L alpha of the membership relation. Okay, and then you take limits at limit ordinals. You take unions of limit ordinals. So in this definition, it's reasonable to ask, do I mean definable over L alpha with or without parameters? Typically people say with parameters. It actually doesn't matter which one you do. You'll still get the same structure in the end. But let's say definable with parameters. So that has the nice effect of ensuring that for all alpha, L alpha is at least a subset of L alpha plus 1. So these levels are increasing. They're all transitive. The way you prove that L alpha plus 1 is transitive is to notice that it contains L alpha, which is transitive by induction, and then it's just adding in a bunch of subsets of that. So that gives you the transitivity of L alpha plus 1. It's a good exercise to do this. The point, the kind of surprising thing here is that if you define L, the constructible universe, to be the union over all alpha, the ordinals of the L alphas, you get a model of ZFC. So it's a proper class model of ZFC, since of course you can't, working within ZFC, you're not going to be able to define a set-sized model of ZFC, since that would contradict the Gödel's incompleteness theorem. But L itself does model ZFC. So what is going on here is you're taking advantage of the fact that the ZFC axioms, when you state the comprehension axiom in ZFC, one would like to assert that whenever you have a set and you have a subset of it, or a sub collection of it, that also forms a set. But you can only really state the first order version of that, which is the first order separation principle. Whenever you have a set and you have a definable sub collection of it, that forms the set. So since we're iterating this first order definability operator, we actually ultimately add in all the definable sub-collections of every set into L. And so this final model L does satisfy the ZFC axioms, even though it might not contain all the sets. So this independence phenomenon that arises, it sort of has to do with the fact that, well, the ZFC axioms, if you state them in the second order way, where you have the full comprehension axiom, it says that given a set, all of its sub-collections form sets. These axioms are categorical, basically, up to the, any two models of ZFC, second order ZFC with the same ordinals are actually isomorphic. So there's no real independence phenomenon for second order ZFC, whatever that means, since there's no proof theory for second order ZFC. But there can be many models of first order ZFC. And L sort of gives you the reason that is. It's easy, much easier to satisfy the first order comprehension axiom. But the interesting thing about L is that it the interesting thing about L is that it's I guess canonical or absolute, in the sense that if you have any two models, M0 and M1, with the same ordinals, so the ordinal numbers that are contained in M0 are equal to the set of ordinal numbers contained in M1, then if you do the construction of L within M0, you can do the construction of L within any model of ZFC, because I just showed you this construction. It's a transfinite construction that provably works in ZFC. Then L of M0 is equal to L of M1. So this model L, it doesn't really depend on the background universe of sets in which it's built. And so even though ZFC is not categorical in some sense, the model L can't really be changed except up to the choice of the ordinals of the model in which it's built. And in practice, this has the effect that every natural question one can ask about L can be decided so not necessarily in ZFC, because ZFC might not be able to tell you about what kind of ordinals exist in L. So there's this problem that L is only uniquely determined up to the ordinals of the model in which it's built. So not in ZFC, but in ZFC plus large cardinal axioms. So for example, ZFC doesn't decide whether L contains an inaccessible cardinal. But of course, ZFC plus an inaccessible cardinal does decide this. So this is just an example why you need this extra large cardinals hypothesis here. But in general, this is not usually that important. So the main point I'm making is that if you ask a question about L, you can typically answer it. So the independence phenomenon, this, we can't decide CH, we can't decide anything. It doesn't apply if you restrict your questions to L. So for example, L is a model of ZFC. So it has something that it thinks is the real numbers, or V omega plus 1. These can all be defined. And you can ask, and it has what it thinks is aleph 1, some cardinal. Whenever you're working in a model of ZFC, you can look at what it thinks are the cardinals. And you can ask, does L satisfy the continuum hypothesis? And Gödel showed that L satisfies not just the continuum hypothesis, but the generalized continuum hypothesis. So for all cardinals lambda, 2 to the lambda is equal to lambda plus. And much more has been done in L. Practically every question of set theory has been decided in this model. There are really it's hard to come up with an open question about the internal structure of L. I mean, I'm sure there are some, but very few. It's the structure of this model. I mean, I think you can start asking really hard questions about L, but it's sort of like doing number theory. You can ask really hard questions about the natural numbers, but they can, presumably, whatever questions you ask, you could either prove the answer is yes or prove the answer is no. I mean, there are just no counterexamples to that in practice, even though we know from incompleteness theorems that there are counterexamples in theory. Okay. So the question raises the question, obviously, maybe we should just stop worrying about V and just work with L, because L is not defective in the way that V is. There's some sort of ambiguity in the conception of the universe of sets V, because we can't say which of these many models it is, but L seems sort of concrete. And maybe just the same way that we restrict to pure sets, we should, instead of allowing, sets that don't appear in the cumulative hierarchy, maybe the same thing should apply to L, and we should just restrict to constructible sets. So the question that this formally I'm asking is V equal to L? Or should we adopt the axiom that V is equal to L? And the thing is, it's consistent with ZFC. That V is equal to L. It's also consistent that V is not equal to L. So why is it consistent that V is equal to L? Well, L turns out to be a model of ZFC plus V is equal to L. So this is a consistent theory. I mean, if ZFC is consistent, which it is, especially in this lecture series, ZFC is very much taken to be consistent, since we're going to be working with large cardinals that prove a whole lot more than that. So so we get there's an obvious natural model of V is equal to L. So it takes a bit of work to show that actually L satisfies V is equal to L. It's sort of standard in set theory by now. It's basically the fact that the construction of L is absolute. So when L tries to construct the constructible hierarchy, it actually constructs the right thing, and it sees that every set appears at some point in the constructible hierarchy, because that's how L was built. I mean, I guess I should say here, it is a bit weird to assume V is equal to F. Model of ZF containing the ordinals. And V, on the other hand, is the maximum model of ZF containing the ordinals. And it sort of maybe seems antithetical to the goals of set theory, which is to understand what it means to collect all the sets, to be sort of minimizing the sets that exist. But I don't know how compelling that kind of argument really is. So let me talk about another argument that V shouldn't be equal to L. So the question, actually, originally the question of whether was an open question until the 60s. And by this, I mean not open in the philosophical sense, but open in a mathematical sense. The issue was it wasn't known how to build any models of set theory that didn't satisfy that V is equal to L. It wasn't known that V is not L was a consistent theory at all. And so the first proof of the consistency of V is not equal to L comes from something called Scott's theorem. So the theorem says, in fact, if there is a measurable cardinal, then V is not equal to L. So if measurable cardinals are consistent, then so is V is not equal to L. Of course, a couple of years later, Cohen proved in ZFC that if ZFC is consistent, so is ZFC plus V is not equal to L. So the idea behind Cohen's proof, I mean, it's just forcing. You take a model of, say, V is equal to L, and you can expand it to a bigger model that satisfies that V is not equal to L, but has the same ordinals. Another way to summarize this proof is you take a countable model of V is equal to L, and you can show that with probability 1, if you pick a real at random, you can actually add it into the model and preserve the ZFC axioms and not add in any new ordinals. So now you have two models with the same ordinals. The first one satisfied V is equal to L, and the second one is strictly bigger. And so that second model has to be a model of V is not equal to L, because it has to compute that L is equal to the original model, right? Because two models with the same ordinals have the same L's. Okay, but Scott's theorem is actually more relevant to us, and it's more relevant to the philosophical question of whether V is equal to L. So let me just remind you, hopefully, of the proof of this. The idea is to use both the characterizations of measurable cardinals. So kappa is measurable. So 1, if kappa carries a kappa complete non-principal ultrafilter, or equivalently 2, if there is an elementary embedding with critical point kappa. So the point is this model M, so M here is a transitive model, a transitive class, contains all the ordinals. So in particular, that means that L of M is equal to L of V, which is L. So to show that V is not equal to L, it's enough to show that M is properly contained in V. So M is not equal to V, because then we have that L is contained in M, is properly contained in V, so V is not equal to L. So that's how this proof works, and the point is, why is that true? Well, actually, let's let kappa be the least measurable cardinal. That makes it a little easier to show that M is not equal to V. The point is that now, because J is an elementary embedding, J of kappa is the least measurable cardinal of M. And we have that kappa is not equal to J of kappa. So that shows that V is not equal to M. Now, since V is the maximal model of ZF, M has to be contained in V. Now we know it's properly contained in V because of this inequality. So being the critical point is what gives us that J of kappa is not kappa. So M is properly contained in V, but we know L is contained in M, and so V is not equal to L. So it uses this fact that, one, we have a first order characterization of measurability, but two, we also have this second order characterization, which gives us this full elementarity. That means that measurability has to be different in M from in V. So the basic point is, once you have a measurable cardinal, you need to have these transitive inner models of V that are not equal to V, and that can't happen if V is equal to L. Okay, so if you accept that measurable cardinals are valid large cardinal axioms, this sort of makes it more reasonable to reject the axiom that V is equal to L than to accept it. And this is actually part of the idea behind that Gödel had. He even himself suggested that maybe one should add V is equal to L into the ZFC axioms to get a theory that is effectively a complete theory of V. What he called it was an absolute notion of provability. So this was going to be ZFC plus large cardinals plus the axiom V is equal to L. But he said, if you really want some absolute notion of provability, it's very important that large cardinal axioms, which he took to be sort of, I don't know, evident, be compatible with V is equal to L. And he mentioned this fact that inaccessible cardinals, for example, are already inaccessible cardinals in L. So this sort of breaks that. And but the thing is, measurable cardinals, I think, especially when you're starting out looking at set theory, it's sort of unclear whether you should really accept that this is a large cardinal axiom, because it's asserting the existence of this non-principal ultrafilter. And why is that? I mean, okay, it's something that's true about omega, right? Omega carries an omega complete non-principal ultrafilter, but is it really a large cardinal property of omega? Maybe this makes it look a little bit more like a reflection principle. And it really, I mean, somehow it does feel like the only way to keep ascending in the large cardinal hierarchy, if you look at things like Malo cardinals and then weakly compact cardinals, it really does feel like the next place to go is measurable cardinals. But you don't really need to go as far as a measurable cardinal to see whether to see to answer the question of whether V is equal to L. So there's actually a large cardinal axiom right exactly at the level of the question of whether V is equal to L. It's called zero sharp. So let me just state this theorem that sort of exactly characterizes a dividing line between the universe when V is close to L and the universe where there are large cardinals that go beyond L. I mentioned this last time too, but since I'm going to be talking later today about Wooden's Hod dichotomy at greater length and actually proving part of that theorem, I thought it's worth going over again. So the theorem, which is from the 70s, is that exactly one of the following holds. One, every set of ordinals A is included in a constructible set so that just means that B is in L. L is the constructible universe. I don't know, the sets in L are called constructible sets, such that cardinality of B is at most the cardinality of A plus Aleph 1. So off by a factor of Aleph 1, maybe you can approximate any set by a set of the same size that's already constructible. Or else, two, there is an elementary embedding J from L to itself. So I guess this part of this theorem is due also to Kunin, if I state it this way. So the dichotomy kind of is that, well, no, I guess this is entirely due to Jensen. So either on the one hand, you have this principle, which is very similar to saying that V is equal to L, right? If we knew that every set of ordinals was actually constructible, then V would be equal to L. Or you have this principle, which is sort of version of there is a measurable cardinal. So it's saying in a much sharper way that Scott's theorem, it's sort of the only reason that that V and L can be very far apart. So if you think about the proof of Scott's theorem, what's really going on is that this embedding that you get from a measurable cardinal, J from V to M, it restricts to an elementary embedding from L to L. And the whole problem was that well, we couldn't have such an embedding if V was equal to L because we were moving where the first measurable cardinal went. Okay, so there's a weakened version, but still quite strong, of measurability, kind of large cardinal axiom, which has constructibility built into it. And then there's this weakened version of V is equal to L. And we know that there are really only two possibilities. Either V is almost equal to L, or there's this weak version of a measurable cardinal. by the way, there's another way to say this that again looks a lot like measurability. Just another way is there's an L ultrafilter, U with a well-founded ultrapower. Well, I can actually even just say there's a kappa complete L ultrafilter on some uncountable cardinal. What an L ultrafilter is, it's just an ultrafilter that measures all the sets in L. It doesn't necessarily measure every subset of kappa, just the constructible ones. So 2 is sort of like saying there's a measurable cardinal relative to L. Okay, I want to talk about the 2 sides of this dichotomy. So first, when L covers V, so the situation when there is no elementary embedding from L to L, and instead every set can be covered by a constructible set. So in this case, you have this consequence, for example, then every singular cardinal is seen to be singular inside of the constructible universe L, and L can actually correctly compute the successor of lambda. So it's L knows a lot about the structure of the cardinals in V. It can correctly compute certain successor cardinals. So the proof is just, well, why is lambda singular in L? Take a set A contained in L, contained in lambda, such that the cardinality of A is less than lambda, and guess A is cofinal in lambda. Okay, and then cover A by some constructible set B in L, such that the cardinality of B is less than or equal to A plus alpha 1. And then B witnesses that lambda is a singular cardinal in L. It's pretty easy to see, just because B has cardinality strictly less than lambda, and it's already cofinal in lambda because A was, and A is contained in B. So notice that this sum A plus aleph 1 is strictly less than lambda. Since lambda is a singular cardinal, lambda is strictly greater than aleph 1, and by assumption, cardinality of A was already less than lambda. So that tells us this first fact, that every singular cardinal is singular in L. So it's important here to notice it really was required that lambda was a singular cardinal, not just a singular ordinal. There will be ordinals that are singular that are not singular in L. Or there will be, but it's consistent that there are, even in this context, where we're in the covering side of the Jensen dichotomy. So how do you show that lambda plus of L is equal to lambda plus, well, otherwise, with lambda plus is some ordinal between lambda and true lambda plus. And then you say, well, what's the cofinality in L of lambda plus? Or what's the actual cofinality of lambda plus? Right? In L, lambda plus of L is a regular cardinal, but in V, lambda plus of L would have to be a singular ordinal. It's not a cardinal at all. So it has to have some cofinality, which is an actual regular cardinal. So let's say that's delta. The issue is that delta is strictly less than lambda, just because lambda is singular. And so delta can't be equal to lambda, and it can't be between lambda and lambda plus of L because there are no cardinals in that region. So delta is strictly less than lambda, so now lambda plus of L. So now you could try to do this whole thing again and take a contained in lambda plus of L with cardinality of A equal to delta cofinal, and then take B in L with cardinality of B less than or equal to delta plus aleph 1 and A contained in B. And now you have a contradiction, right? Because B is witnessing in L that delta, lambda plus of L is a singular ordinal, and that's impossible because this is strictly less than lambda plus, strictly less than lambda. Okay, so in this situation where you have covering, L correctly computes all successors of singular cardinals. On the other hand, if there is a J from L to L, then every cardinal, every infinite cardinal is an inaccessible cardinal. So this is, I think this is really due to Kunin. It was, so this involves the concept of zero sharp, which was introduced by Silver. So one way of thinking about this is that the cardinals aleph alpha for alpha greater than 1 form a class of order indiscernibles. For L in this context. That means that anything that's true about some sequence of cardinals, some increasing sequence of cardinals in L is actually true about any increasing sequence of cardinals the same length. So you can't distinguish between these cardinals, and that means that, for example, aleph 1 and aleph omega have all the same properties in L. So that means since aleph omega is a limit cardinal, aleph omega is a limit cardinal in L. That's a downwards absolute property. So anything like that holds in V has to hold in L. And that means that aleph 1 is a limit cardinal in L. So that's this indiscernibility. And therefore, aleph 1 is a regular limit cardinal in L, so it's inaccessible. But that means that every cardinal is inaccessible in L, because every cardinal has all the same properties that aleph 1 has in L. And you can keep going like this. Well, aleph omega is a limit of cardinals. So that means that in L, it's a limit of inaccessible cardinals. So that means that aleph 1 is a limit of inaccessible cardinals, and so on. Okay, so every cardinal is a limit of inaccessible cardinals in L. And in the end, what you will see is that every cardinal has every large cardinal property. Compatible with V is equal to L. So in L, these kind of statements are a little hard to parse. So what I mean is, if you take a cardinal in V, like aleph omega, then it will appear in L that this cardinal, some ordinal, and L contains all the ordinals, so it can look at this ordinal. This ordinal will appear to have any large cardinal property you can imagine that doesn't go beyond L. So it's not like these cardinals will appear to be measurable in L, because if L thought that there was a measurable cardinal, you would have a big problem. You'd be refuting whatever large cardinal hypothesis you assumed by Scott's theorem. But they will seem to be weakly compact and subtle and ineffable and a million other large cardinal properties that it can actually hold in L. Okay, so what's zero sharp? Zero sharp is just the name for this large cardinal property. There is an elementary embedding J from L to L. So it's much weaker than a measurable cardinal. But on the other hand, it's kind of getting there. Sort of, it's the first large cardinal property beyond L. So it turns out if zero sharp exists, or in other words, there's an elementary embedding from L to L, one can actually classify all the elementary embeddings. From L to L. So there's actually a very simple theory that tells you everything you could want to know about elementary embeddings from L to itself. It's related to this order indiscernibility. Basically, what you do is you get a maximal class of order indiscernibles, and it turns out that every elementary embedding from L to L is formed by just taking some subclass of this class of indiscernibles and moving the class of indiscernibles to that subclass. But the point I'm trying to make is just that these embeddings are very well understood if they exist. They're not mysterious in the same way that measurable cardinals are. So for a measurable cardinal to exist, you have to assert the existence of this kappa complete ultrafilter on kappa. And that's a very mysterious object. There's not that much you can say about it. It's not necessarily unique. On the other hand, if the elementary embeddings from L to L are sort of, not just sort of, they are canonical objects. If there is one, you can define a specific one, simplest one. So there's some simplest embedding from L to L. And you can actually use that embedding to generate a canonical model of set theory beyond L. So remember I said that that L is canonical, and this was in the sense that any two models with the same ordinals computed the same L. And every question you could ask about L, you could also answer within ZFC plus large cardinals. So the claim is that using this very simple embedding from L to L, you can build the next model beyond L. So what is the next model? One way to write it is as L of J. So this is just defined by adding into the construction of the constructible hierarchy a predicate for this simple embedding J. So you start with L0 of J. Let me just start a new page. That's just the empty set. L alpha plus 1 of J. This is just the set of all definable subsets of the structure L alpha of J with membership and also J restricted to L alpha of J. So you're adding in a function symbol if you want for J. And then everything else is exactly the same as the construction of L. And what you get is a model L of J, the union of all these levels. An L of J is a model of ZFC plus V is not equal to L. And it satisfies that 0 sharp exists. And the reason is just that, well, we put J into L of J. And so L of J will see that there's an elementary embedding from L to L. And L of J will be the minimum model of ZFC that satisfies this principle. So if you have if you have any model of ZFC that contains all the ordinals and satisfies that there is an elementary embedding from L to L, then it will be equal, or it will contain L of J. That's why I had to pick the simplest embedding J. If you try, there are many different embeddings from L to L, even though there's a classification of them. You can encode anything into an embedding from L to L. So you could find a J such that L of J contained any set that you want. So you have to sort of carefully choose J to be as simple as possible. But if you do that, then you do get a canonical model of set theory. It satisfies GCH, and there's even an analog of the covering theorem for L of J. So there's this relativized version of Jensen's theorem. Again, exactly one of the following holds. One, there is an elementary embedding I from L of J to L of J. Or 2, every uncountable, well, every set of ordinals is contained or included, whatever you want to say, in some set B in L of J, such that cardinality of B is less than the cardinality of A plus L. So there's this hierarchy of models that's beginning to emerge. If you look at this phenomenon, you could take the simplest embedding from L of J to L of J and then form the model L of J and I. And this would give you a new model that's strictly larger than L of J. And that also has this version of the covering lemma. So the basic feeling in set theory is that in all these cases, what should happen is that there really is an elementary embedding from this model to itself. This next canonical set really does exist. The reason for that is, well, otherwise you're basically assuming that V is equal to L of J, but we sort of have a pretty good understanding of the embeddings from L of J to L of J if they exist, and they really do seem like the next large cardinal beyond L of J. So probably shouldn't restrict yourself to here. You get the next embedding, you get the next canonical model, and you get this hierarchy of models that's building up more and more large cardinals. This hierarchy actually eventually reaches all the way to build a canonical model that has a measurable cardinal in it. So you eventually get to the level of Scott's theorem, and you keep having covering theorems for all these models. And the question is, how far do these models go? So which large cardinal axioms have canonical models? And for all we know, maybe all of them do. So that there's this canonical model at the level of a measurable cardinal. So there's a, if you have a measurable cardinal kappa, there's actually a minimum model of ZFC in which kappa is a measurable cardinal. And this is a model of GCH. You can answer any question you want about it. You get a unique measure on kappa in the model. It's all a very nice theory, and it would be a remarkable property of large cardinal axioms if they really all had canonical models. Models about which you could answer every question. I mean, this just, it doesn't, if you pick an arbitrary statement, an arbitrary set theoretic principle, it just doesn't happen that the principle necessarily has canonical models. Of course, for something like GCH, well, all of the canonical models satisfy GCH, but typically the models that you wind up building for various set theoretic principles that come up are very far from being canonical. They're pretty ad hoc. Whereas we have this hierarchy of canonical models that eventually satisfy all of the large cardinal axioms we're interested in. So maybe all of them do. The canonical models that are known today reach up past strong cardinals, which I discussed a little bit last time, and they appeared prominently in the exercises. So hopefully you know and love strong cardinals at this point. And they reach into the hierarchy of wooden cardinals. So actually, the canonical models that are known reach high enough to contain large cardinals that are strong enough to prove all the determinacy theorems that I talked about last time. So there are canonical models in which L of R satisfies the axiom of determinacy, which is a very strong principle. And it is quite amazing that you have these generalizations of L that are big enough to have the sort of correct theory of L of R in them. And the theory of canonical models has actually become an important part of the analysis of L of R. So it has applications outside of just building these canonical models. It's also the key to gauging the strength of theories that arise in set theory. So if you want to understand what the large cardinal strength of a theory is, so what large cardinals are required to prove the consistency of a theory, the way this always works, it seems, is to start with your set theoretic principle that you're trying to understand and use it to produce canonical models of large cardinals. So if the principle seems to require a measurable cardinal, for example, then often what will happen is you start with the principle and you can show using the principle somehow that there has to be a canonical submodel of the universe with a measurable cardinal. One very, far off in the future kind of question is whether one could build an ultimate, largest sort of canonical model. I'm trying my best not to say the phrase sort of. I feel myself saying sort of about once every 2 minutes. And I know that must mean that I'm saying it 4 or 5 times every 2 minutes. So just pay attention, and you can use some sort of Zoom reaction every time I say sort of, to try to, as if I had a shock collar or something. Okay, so is there an ultimate canonical model? This would be is there, so similar question, what does ultimate mean here? Is there a model that's canonical in the sense that L is canonical, so you can answer all the questions you want about it, and its construction doesn't really depend on the background universe in which you construct it, but it should provably cover V in some sense. So it should automatically be on the good side of the Jensen dichotomy, on the side where the model is large, or in other words, a model M such that there is no from M to M, no elementary embedding from M to M. So Scott's theorem doesn't apply to this kind of model. And the idea is that if you could build a canonical model that contained all large cardinals, so if you could solve this question of how far the inner models go, and if the answer was they go all the way, every large cardinal has an inner model, then you should be able to build a model that doesn't have an elementary embedding to itself, because that would be some sort of large cardinal beyond it. And you should be able to build in that case, if this covering phenomenon continues, then maybe that model provably has has a covering property with respect to V. So this is very speculative, but if that were the case, you would have some sort of deeper analysis. A deeper analysis of V. It would tell you that inside of V, there's this model that you can analyze completely, and that is combinatorially close to V. It would allow you to prove new theorems about V, but it would also suggest an axiom that V is equal to the model. So it could this axiom wouldn't be vulnerable to the kind of attack that the axiom V is equal to L is vulnerable to, because there would be no large cardinals outside of the model M. So this is sort of the idea behind Wooden's ultimate L program. And I'm going to be talking about today the Hod conjecture, which is a conjecture that's related to this question of whether there's a model that provably, a canonical model that provably covers V. The Hod question that I'll talk about after the break, it's a test question for whether there could be a model like this. Because at this point, the things I'm saying are starting to be hopelessly vague. I'll focus instead on a question that's completely precise, and it seems that this question encapsulates the question of whether, not encapsulates, but it gets close to capturing the question of whether there could be a canonical model that covers V. Okay. Let's break now before I start talking about new things. Okay, we left off, and I was making some vague pronouncements about the existence of an ultimate canonical inner model. But how do you even make the question precise? One way to do that is Wooden's Hod conjecture. So let me remind you what Hod is. So I think I said it yesterday, but I was sort of quick. A set is OD if it is definable in the structure V with membership from ordinal parameters. So this concept is also due to Gödel. The interesting thing here is that ordinal definability is actually formalizable in a first order way. The point is, set is actually OD if and only if it is definable from ordinal parameters. In V alpha for some alpha. So definability over this structure V with membership is not a first order property. You can't write down a formula that will hold of exactly the sets that are definable in V. So definability is undefinable. It's a bit like the undefinability of truth. But sort of paradoxically, this stronger concept of definability that allows all ordinal parameters is definable. And a way of seeing why you have to move to all ordinal parameters is, well, if you don't allow ordinal parameters, then you can think about what is the least undefinable ordinal. If you had some formalization of definability that was definable, then you would be able to define the least undefinable ordinal. But then it wouldn't be undefinable, so that would be a contradiction. But now with ordinal definability, that kind of paradox just goes away. So this gives you a first order way to talk about ordinal definability in set theory, and it's quite useful because it makes many questions about definability actually first order questions. They're just questions about definability in levels of V. So why does this equivalence work, by the way? Well, if X is ordinal definable in this more abstract sense, then it should be definable. So intuitively, then it is definable by a sigma n formula from some ordinal parameters alpha vector. So what you can do is just choose an ordinal alpha greater than alpha vector such that V alpha is a sigma n elementary substructure of V. The point is, by the reflection theorem, there are arbitrarily large such ordinals alpha. And now our ordinal definable set X will be definable in V alpha from alpha. So conversely, it's pretty obvious that if a set is definable from ordinal parameters in some V alpha, then it's definable over V or in V, because V alpha is itself ordinal definable. So you can ordinal define V alpha and then use V alpha to ordinal define X. So X will be ordinal definable. So these two characterizations are equivalent. The ordinal definable sets give rise to a kind of generalization of L, and a transitive model that contains all the ordinals, but it's typically much bigger than L. This is called HOD. So HOD is equal to the collection, the class of all sets X, such that X is OD, but also every element of X is OD. And every element of X is OD. Seem to be unable to spell element. And so on. Or in other words, it's the set of all X such that the transitive closure of X, union X, is all contained in the OD sets. Another way to say it, finally, is that HOD is the largest transitive class that's contained entirely within the OD sets. So every element of HOD is OD, and HOD is a transitive class. And it turns out that for reasons very similar to the reason that L is a model of ZFC, HOD is a model of ZFC. But the big difference between HOD and L, well, one of the big differences is that HOD is not canonical. So first, the HOD of different models of set theory can vary wildly. So even if the two models have the same ordinals, they might have very different ordinal definable sets. And it's intuitively sort of clear why that is. The definition of Hod it's not about first order definability, it's really definability over the whole universe. So it makes sense that Hod would depend a lot on what universe it's constructed in. And basically for this reason, essentially no questions about Hod can be answered about the internal structure of Hod can be answered that couldn't already be answered in ZFC. And there's a way one can actually formalize this. I can't remember who this theorem is due to, but it's a great theorem. So I'm sorry to them, but they were working in the 1960s or 70s, so probably they will forgive me, or they won't know that I didn't remember who proved their theorem. So the theorem says if phi is a sentence, then the following are equivalent. So one, ZFC proves that Hod is a model of the sentence phi. So it's provable, if it's provable in ZFC that Hod satisfies this sentence phi, then in fact, ZFC already proved phi. Okay, so there's nothing you can prove about the internal structure of Hod that you couldn't just prove in ZFC. So you can change this a little bit, sort of interesting also. This doesn't really strengthen the point I'm making, but ZF already implies that Hod is a model of the axiom of choice. And it turns out that that's all ZF implies about Hod. So Hod is sort of a generic model of choice from the perspective of what can be proved in ZF or ZFC. So remember the Jensen dichotomy for L, this covering property compared, or this strong dichotomy about whether L is close to V or far from V in terms of large cardinals, it seems to be a property or a characteristic property of the canonical models, that they have these covering dichotomy theorems. So it was pretty surprising when Wooden showed that in the context of large cardinal axioms, Hod has a dichotomy theorem as well. The theorem is, if kappa is extendable, and I'll tell you what an extendable cardinal is in a second, then exactly one of the following holds. One, well, first option is that Hod covers V above the extendable cardinal. So this says if A is a set of ordinals, then there is an OD set such that A is contained in B, and the cardinality of B is not too much larger than A, at least relative to this extendable cardinal. So remember, in the Jensen dichotomy for L, the covering was quite a bit better. Instead of an extendable cardinal here, you just had Aleph 1. So the covering that takes hold for Hod really can only happen above large cardinals. And it really is consistent that covering fails for Hod below these large cardinals. So this is really an asymptotic property of ordinal definability. It only starts to take hold way up high in the universe of sets. Second property, the second possibility, well, it's the question about, you might hope that you could get here, there is an elementary embedding from Hod to Hod. You can't do that, but there are many open questions about how close to that you could actually get. All I'm going to say here is another version of the other side of the Jensen dichotomy, remember, was that every infinite cardinal is inaccessible in L. And here what you can get is that every regular cardinal above kappa is measurable in Hod. So measurable cardinals, they're not just inaccessible, they're limits of inaccessibles. They're really pretty big. So it looks like every regular cardinal is inaccessible in Hod. And these really are mutually exclusive. If you remember the proof I gave that singular cardinals are singular in L and their successors are correctly computed if L covers V, exactly the same proof will show you that if Hod covers V, even above this extendable cardinal, then all singular cardinals above the extendable are singular in Hod, and their successors are correctly computed. So we have lambda plus Hod is equal to lambda plus V by Hod, assuming Hod covers V. And if you have this, then lambda plus, which is a regular cardinal in V, is not measurable in Hod. It's not inaccessible because it's a successor cardinal. So 1 implies the negation of 2. So I want to explain how this relates to the question of an ultimate inner model, and then I'm going to sketch part of the proof of this theorem. And I guess I can tell you what an extendable cardinal is. The definition is not too complicated, although I'm going to probably work with a slightly different large cardinal hypothesis just because it's weaker and you don't need an extendable for what I'm going to do. So kappa is extendable if for all alpha greater than or equal to kappa, there is some alpha prime greater than alpha, and an elementary embedding J from V alpha to V alpha prime, such that the critical point of J is equal to kappa. And really that's all I need to say, but just to make myself happy, I'll say J of kappa is bigger than alpha. This is not really required. The hypotheses are equivalent. If you think about it, this has something to do with the Kunin inconsistency theorem I was talking about last time. In the context of ZFC, it doesn't matter if you say that J of kappa is bigger than alpha. It's a reasonable exercise. They're the same, they're equivalent definitions. Okay, so this is the large cardinal hypothesis. It's really a very strong large cardinal hypothesis. The inner models for extendable cardinals are canonical models for extendable cardinals, have not been built yet. So we're really looking very high to get this sort of covering property for Hod. So how does it relate to this question of an ultimate inner model? The idea, if there is a canonical model that covers V, then this model should be contained in HOD. So the typical behavior of canonical models is that they have canonical well-orderings. Like, for example, L can be well-ordered by looking at where a set appears in the constructible hierarchy. So what's the first level L alpha, such that the set appears as a definable subset of L alpha. And then you can well order all of those definable subsets of L alpha as well, because you can order all the formulas that define them, and you can already have ordered the parameters that they're being defined from. So that gives you a canonical well order of L. And so that means that every element of L is definable from its rank in the ordering. So you can talk about the alphth element of L for any ordinal alpha. And so the alphth element of L is certainly ordinal definable because it's defined from alpha. So that means that L is a subset of HOD. It's a transitive class that's contained inside of the ordinal definable sets. So it's contained in this maximal transitive subclass, the ordinal definable sets, HOD. And this generalizes to all the canonical models that are known, and sort of the concept of canonical contains within it this idea that the sets in the model are well ordered. But let's see. So if HOD contains a model that covers V, then HOD would cover V, because every set of ordinals in V would be covered by a set in this canonical model, and then that would be covered in HOD. But we don't need a precise definition of what a canonical model is in order to ask whether HOD covers V. So this allows you to state a precise test question for this question of whether there's a canonical model of set theory that covers V, even without knowing exactly what you mean by a canonical model. And the HOD conjecture states that in the context of large cardinals, so an extendable cardinal, say, HOD covers V. So in the next hour, I'm going to give part of the proof of the HOD conjecture, but I want to talk about how it's relevant to the question of choiceless large cardinals I discussed before. Point is, under the choiceless large cardinal axioms, HOD, which itself is you can still define HOD in ZF, that's fine. So even if you've dropped the axiom of choice and you're looking at these very strong choiceless large cardinal assumptions, you can define HOD, but HOD is a fairly small model. And Wooden showed that starting from a model M of the choiceless large cardinal axioms, so very strong choiceless large cardinal assumptions, one can use forcing to build an extension of M such that N satisfies ZFC, and the HOD of N is actually a submodel of the Hod of M. So you've extended M, but you've only shrunk Hod. So now you have a model of ZFC where Hod is an even smaller model. And because Hod was so small here that the Hod conjecture was failing in this choiceless context, you now have a model of ZFC, say, plus whatever large cardinal axioms you want. You can preserve the large cardinal axioms when you build N. But Hod of this model is so small that the Hod conjecture is failing there. So this shows that the Hod conjecture could consistently have a negative answer as long as the choiceless cardinals are consistent. So another way to look at it is, if the Hod conjecture is true, it's provable, then the choiceless large cardinals are not consistent. You have to, so gauging what the answer to this question is, really seems to hinge on the consistency of the choiceless large cardinal axioms. Although it's an open question whether the Hod conjecture really requires such strong principles to prove its consistent failure. Okay, but let me get back to the Hod dichotomy theorem. So I'm going to prove a weaker version. What I want to prove is actually the following theorem, which involves the concept of a supercompact cardinal. Kappa is supercompact if for all lambda greater than or equal to kappa, there is an elementary embedding from V into a transitive proper class model of ZFC such that J of kappa is greater than lambda and M is closed under lambda sequences. So whenever you have a function from lambda into M, that function is actually an element of M. So the theorem I want to prove is that if kappa is supercompact, then one of the following holds, exactly one of the following holds. So one, all sufficiently large regular cardinals are measurable in Hod. Two is that every set sigma contained in the ordinals with cardinality sigma less than kappa is covered by some ordinal definable set tau, which also has cardinality less than kappa. So this is a much weaker theorem than Wooden's theorem. It uses a weaker hypothesis as well. And in fact, you can improve this to get much closer to Wooden's theorem. Here you could get that actually all singular cardinals are singular, all singular cardinals above kappa are singular in Hod, and their successors are correctly computed by Hod. And you could get that, in fact, you could get this for any strong limit cardinal above kappa, it's an open question whether just from a supercompact cardinal you could get this full covering property that that you got in Wooden's theorem. So that's kind of a nice open question, I think. Could be not too hard to prove that if kappa is supercompact, then you actually get the full Hod dichotomy. So covering here and measurable cardinals here. But anyway, I'll leave getting improvements of this for the homework because, well, in the interest of time, so there's only 45 minutes left. So what's the key idea in this theorem? It has to do with stationary sets and partitions of stationary sets. So Solovay showed that for any cardinal, any regular cardinal delta, and any stationary set, S contained in delta, there is a partition S alpha, or alpha less than delta of S, into stationary subsets. So this means if you take any stationary set and any regular cardinal, you can always split it into more stationary sets, into two stationary sets if you want. And this is not always obvious. So for example, even splitting omega 1 into two disjoint stationary sets, it's not clear how to do that. And as I mentioned last time, there's a reason it's not clear. It's because of another theorem of Solovay, which says that, for example, in the case of omega 1, there is no partition of omega 1 into disjoint stationary sets S0 and S1 that both belong to the inner model L of R. So in some sense, the stationary splittings of omega 1 have to be pretty complicated. They can't be definable in this sense. So if you look at the proof of Solovay's splitting theorem, it pretty heavily uses the axiom of choice. And the reason, I mean, so it's not constructive. And the splitting problem asks, so for ordinal definable sets, so can an ordinal definable stationary subset of a regular cardinal be split into ordinal definable stationary subsets? Or more generally, is there an ordinal definable splitting of the set into stationary subsets? It's stronger to ask that in the case where you're looking for a transfinite splitting. So a key set to split, a set that does not admit any obvious definable splitting, is the set. So whenever you have an uncountable regular cardinal, so delta is greater than omega 1, you can split delta into some stationary sets, because delta is equal to the union of the set of ordinals alpha, so the cofinality of alpha is equal to omega, plus the alpha, the cofinality of alpha is equal to omega 1, I guess, plus all the successor ordinals, but let's ignore those. These are both stationary sets. So that does allow you to partition, I guess, the limit ordinals into two stationary sets. Okay, so this is, it's not quite equality because I took out all the successor ordinals, but that's a non-stationary set anyway. So I'm only interested in things modulo a non-stationary set. So on the other hand, it's not clear that this set can be split any further into stationary subsets. And so if this set, this is called S delta omega, it's the set of cofinality omega ordinals. If S delta omega cannot be split in an ordinal definable way into stationary subsets, that means that delta is measurable in HOD. So this is how measurability in HOD is going to come up. If you can't split S delta omega into two stationary subsets, delta must be measurable in HOD. Why is that? Well, look at the club filter, or the omega club filter, I guess. Let F be the filter consisting of all sets A containing this regular cardinal delta, such that A contains an omega club. It's an omega club, a set C, such that for any sequence alpha C, alpha n, contained in C, the supremum of the alpha n's is in C. So a set's omega club if it's closed under omega increasing sequences. So it's closed under taking the supremum of any countable subset. Or equivalently, so this filter is the same as the set of all the set of all A contained in delta, such that there is a club, so a fully closed, unbounded subset. Yeah, so this should say an unbounded set. A club C, such that C intersect S delta omega is contained in A. So these are two different characterizations of the omega club filter. So if S delta omega cannot be split into disjoint OD stationary subsets, then F intersect HOD is a delta complete non-principal. Ultrafilter on delta in HOD. So the first point here is that F intersect HOD is actually in HOD. The reason is that F is ordinal definable. It's just definable from delta. It's the omega club filter on delta. That's a definition of F. And HOD is also definable. So F intersect HOD is definable And so F intersect hot is also ordinal definable. It's delta complete because the club filter is closed under intersections of size less than delta. And it's non-principal, because it doesn't contain any bounded subsets of delta, because we're talking about closed unbounded sets. But the reason it's an ultrafilter, so that means it measures every subset of delta, is just this splitting property. So if A is an OD set, so if A is any subset of delta that's in HOD, or equivalently, it's an OD subset of delta, then the claim is that either A or its complement contains an omega club, and the reason is just otherwise, every omega club meets A, and every omega club meets complement. And it follows that A intersect S delta omega and A complement intersect S delta omega are disjoint stationary subsets of S delta omega. Since we assume that there were no such sets, that's a contradiction. So we get that this filter F intersect HOD is an ultrafilter in HOD. So it witnesses that delta is a measurable cardinal in HOD. More generally, we say that delta is omega strongly measurable in HOD if for some gamma less than delta, with 2 to the gamma of HOD less than delta, delta cannot be split into gamma. Sorry, not delta, S delta omega cannot be split into gamma stationary sets. In an ordinal definable way. So there's no ordinal definable sequence of stationary subsets of S delta omega of length gamma. And it's a fact which will be on the homework. It's a bit harder than what I just did, that if delta is omega strongly measurable in HOD, then in fact delta is measurable in HOD. So even though S delta omega may split into 2 stationary sets, if it doesn't split into a lot of stationary sets, basically something like the HOD logarithm base 2 of delta many stationary sets, then you can actually find, what you do is you start with S delta omega and you try to split it into 2 stationary sets, and maybe you can do that. But then you try to split those and those into more stationary sets, and you build this tree of splittings of S delta omega. And you can show that if this process ever stops, then you've built sets that can't be split into more stationary subsets. That gives you, by the same argument as before, the fact that delta is measurable in Hod. And if this process never stops in gamma stages, you can show that you get a partition of S delta omega into gamma many stationary sets. So that's the idea behind this fact, but you'll see the details in the exercises. Okay, so I want to show you how this is related to the choiceless cardinals now. So this is the wooden proof of the Kuhn inconsistency theorem. So the theorem says, remember that there's no elementary embedding from the universe of sets to itself, except for the identity. So Wooden's proof, it uses Solovey's splitting lemma. So let S alpha, so first of all, remember the key ordinals in this proof. So remember, let kappa 0 be the critical point of J, and let kappa n be the nth element of the critical sequence of J, which was the result of applying J n times to kappa. And then kappa omega, or lambda, is the supremum of the kappa n's. So J of lambda is equal to lambda. And lambda is a cardinal of cofinality omega. And the regular cardinal I want to look at is lambda plus. So let S alpha, for alpha less than lambda, be a partition of S lambda plus omega, the cofinality omega ordinals below lambda plus, into stationary sets. Then what you do is look at the partition T alpha for alpha less than lambda, which is given by just applying this embedding to the sequence of stationary sets S alpha. Okay, by elementarity, this is again a partition of lambda plus into stationary sets, because J of lambda plus is equal to lambda plus. So we're just using the fact that J is an elementary embedding from V to V. So these properties, like being a partition into stationary sets, a partition of S lambda plus omega into stationary sets, are all preserved by J. Now the point is that that T kappa, where kappa is the critical point, J has to actually intersect J image lambda plus. The reason is that J image of lambda plus is omega club in lambda plus. So whenever you have a stationary subset of this set S lambda plus omega, it has to meet every omega club subset of lambda plus. And that's because of this fact I mentioned before, that the omega club filter is the same as the club filter restricted to ordinals of cofinality omega. So this is something, it's worth checking this. It's a useful fact. So these two filters are the same, and that implies that a stationary subset of the coph omega ordinals has to meet every omega closed unbounded subset of lambda plus. So J image lambda plus is unbounded in lambda plus, and that's just because j of lambda plus was equal to lambda plus. So we've got this function, it's an increasing function from lambda plus to lambda plus. And so its range, j image lambda plus, has to be cofinal. And on the other hand, it's omega closed because of this property that if you have a sequence of ordinals alpha n for n less than omega, j of the supremum, well, okay, so say you have a sequence of ordinals alpha n, then j of the, let me show you this on another slide. If you have a sequence of ordinals alpha n, this is just to show that j image lambda plus is an omega club. So if this is contained in j image lambda plus, that means that alpha n is equal to j of beta n for some unique beta n, right? Because alpha n is in the range of j, and j is an injective function, so we can choose this beta n sum. Okay, well then the supremum of the alpha n's for n less than omega is equal to the supremum, the j of beta n's for n less than omega, which is equal to j of the supremum of the beta n's for n less than omega. So that means that this supremum is in j image of lambda plus. So that shows that j image of lambda plus is omega closed. That was the definition of omega closed. Anyway, this is just to justify this fact that actually all of these sets, all of these stationary subsets of S lambda plus omega have to intersect J image of lambda plus. But the problematic one is going to be T kappa. So T kappa intersect J image lambda plus is not the empty set. So that means there is some ordinal alpha in this intersection. So it's of the form J of beta, such that alpha is in T sub kappa. Now, alpha is in S lambda plus omega, so by elementarity, its preimage beta is also in S lambda plus omega. And so since S lambda plus omega was the union of these lambda many stationary sets, S sub xi for xi less than lambda, we have that alpha is in S sub xi for some xi. Beta is in S sub xi for some xi. And now that means that J of beta is in J of S sub xi. And by elementarity of J of S sub xi, the J of the xth element of this partition has to be the J of xth element of the image partition, the T's. So this is equal to T sub J of xi. Okay, so where are we now? We have this ordinal alpha, which is both in T sub J of xi and in T sub kappa, where remember this T sub xi for xi less than lambda was equal to J of our original partition. So there's a problem here. These sets are supposed to partition lambda S lambda plus omega. So in particular, they're supposed to be disjoint. They can't be disjoint because these two sets have an element in common, even though their indices are different. Remember, kappa is supposed to be the critical point of J. So kappa is not equal to J sub C. So that's a contradiction because we just found two elements of our partition that are not disjoint. So that's Wooden's proof of the Kunin inconsistency theorem. So remember, I defined supercompact cardinals by this definition in terms of the elementary embeddings. So kappa is supercompact if for all lambda greater than or equal to kappa, there's a J from V to M with M to the lambda contained in M, and J of kappa is greater than lambda, and critical point of J is equal to kappa. I think I wrote the conditions in exactly the reverse order the previous time. Now, the proof of Wooden's theorem that I just gave is actually closely related to the theory of supercompact cardinals. And the reason is that one can show that if delta greater than our supercompact cardinal is regular, and S alpha for alpha less than delta, or say for any length gamma, is a partition of S delta omega into stationary sets, then what's known as Solovey's lemma tells us that for any J from V into M, J image as ordinal gamma is precisely equal to the ordinals alpha less than J of gamma, such that, let me write out my hypotheses on this slide as well. So suppose gamma is less than delta, delta is regular, and S sub C for C less than gamma partitions S delta omega into stationary sets. So let J from V to M be an elementary embedding, and let T sub C for C less than J of gamma be the image of these stationary sets under J. So now that J is not an elementary embedding from V into V, there's no reason to think that all of these are actually stationary subsets of J of delta. Okay, so this is just some sequence of subsets of J of delta, and it's not clear which ones are actually stationary. So the key ordinal to look at is actually the supremum of J on delta. So this is the ordinal where we know that that J image delta is an omega club subset of delta star. Then Solovey's theorem says that J image of delta is actually precisely equal to all of the Xi less than, J image of gamma is equal to all the Xi less than J of gamma, such that T sub Xi, this image fake stationary subset of J of delta, intersect delta star is stationary as a subset of delta star. Okay, so J image gamma, the range of J on gamma is actually definable from this sequence of fake stationary sets and this ordinal delta star. Sort of surprising that you can recover J image gamma in such a uniform way. It doesn't really depend on J at all, except for how J moved this sequence of stationary sets. And the proof actually just comes right out of looking at the proof of Wooden's theorem on the Kunin inconsistency. What we actually showed was that if because T sub kappa was stationary, kappa had to be in the range of J. That was how the proof worked. And that's a contradiction because kappa can't be in the range of J. But if you want to actually get something out of that, that's not just a contradiction, this is what you ultimately get. You get that the points in the range of J are exactly the places where these image points, the points in the image stationary partition are stationary in this ordinal coming from the omega club J image delta. So that's Solovey's lemma. And let me show you how you can use that to get this version of the Hod dichotomy theorem. So remember, what is it that we want to prove? So the theorem is, well, what I'll actually show is if kappa is a supercompact cardinal, then one of the following holds. One is that every set tau contained in the ordinals with tau strictly less than kappa is contained or included in set sigma in Hod with cardinality of sigma less than kappa. So it's this covering property for less than kappa sized subsets of the ordinals. Or two, there is some ordinal gamma such that for all regular delta greater than gamma, next page, delta cannot be split into a gamma sequence. Okay. S delta omega cannot be split into a gamma sequence of stationary sets. Okay, so this is even stronger than saying delta is omega strongly measurable in Hod, because there's this uniform gamma, this one fixed ordinal gamma, such that for all the regular cardinals above it, you can't split even into gamma many stationary sets. And the nice thing about this is, remember, in the definition of omega strongly measurable, there was something about 2 to the gamma in Hod being less than or equal to delta. Well, if we go up to a big enough regular cardinal, since we just have this one fixed gamma, we're definitely going to get this property to hold. Just that'll eventually hold for all delta, just go up above this ordinal. So it makes it a little simpler to think about. So the point is, either we have this version of covering, which actually implies much stronger covering properties for Hod, you'll see in the homework, or there's this uniform ordinal gamma so that regular cardinals can't be split into gamma many stationary sets. So the proof is actually not so hard now. So suppose that 2 fails. So in other words, there is an ordinal, there is, for each ordinal gamma, sorry, love negations. There is some delta greater than gamma, regular cardinal, such that S delta omega can be split into gamma many stationary subsets. And I want to show that that we have the covering property. So given this, for some gamma, I want to show that every less than kappa size subset of gamma can be covered by an OD set of size less than kappa. Okay? So fix gamma and its corresponding delta. And I'm going to show that for any sigma contained in gamma with cardinality of sigma less than kappa, there is an OD set tau contained in gamma with cardinality of tau less than kappa and sigma contained in tau. So how to do that? Well, we can fix by our assumptions on gamma and delta. I'm going to fix an OD partition S sub c for c less than gamma of S delta omega into stationary sets. And since kappa is a supercompact cardinal, so kappa is, you can think of kappa as being way down below everything in sight. It doesn't actually matter here. So let me draw the picture though. So we've got kappa down here, then we've got gamma, we've got delta. So since kappa is supercompact, we can find an elementary embedding from V into M so that M is closed under delta sequences. Okay, so we have this splitting of S delta omega over on the V side of things. And that gets mapped up by this embedding J to some sequence T sub C for C less than J of gamma. And Solovey's lemma says that if we look at these sets T sub C, the Xi that belong to the range of J are exactly the Xi such that T sub C is a stationary subset of this ordinal, the sup image of delta. So let me try to draw this a little bit more clearly. So this ordinal here is going to be the key, delta star. So Solovey's lemma tells us that J image gamma is equal to the set of all Xi less than J of gamma, such that T sub Xi intersect delta star is stationary in delta star. But the thing is, since m to the delta is contained in m is correct about what subsets of delta star are stationary. It's because the stationarity in an ordinal delta star of cofinality delta only depends on stationarity and its cofinality. Stationary sets really only talk about regular cardinals. So you can talk about stationary subsets of a singular ordinal, but it really only depends on some club subset of delta star of order type delta. So it doesn't matter when you define J of gamma this way, it doesn't matter if you write that T sub C intersect delta star is actually stationary, or if you write that M satisfies that it's stationary. So that's also something that's on the homework. But it's pretty easy to see. Okay, so since M is closed under delta sequences, we can actually characterize J of gamma inside of M using this sequence of stationary sets. But now, look, we had this splitting that's in Hod, and this splitting is in Hod of M, which might be a different model. But anyway, what this is showing is that J image gamma is itself definable in M. It's OD in M because we use this definable sequence and then we use this ordinal delta star, and together they defined J image gamma. So that gives us that J image gamma is ordinal definable in M. So we have this sequence of M stationary sets, and we have some ordinal in M. And by looking at where these sets reflect, so which indices give you a stationary subset of delta star, we can compute what J image gamma is. Okay, so why is that useful? How does this finish the proof? So fix some sigma subset of gamma with sigma cardinality less than kappa. And we want to show that sigma can be covered by an ordinal definable set of size less than kappa. So it suffices to show that J of sigma can be covered by some tau in M, such that tau is in Hod of M, and tau has cardinality less than J of kappa in M. Right? Then by elementarity, sigma can be covered by some set tau that's in the true Hod that has cardinality less than kappa. But J of sigma is actually contained in J image of gamma. The reason is that since sigma has cardinality less than kappa, that actually implies that J of sigma is just equal to J image sigma. This is an important property of elementary embeddings. If you take a set of size smaller than the critical point of J and you move it by J, all that happens is you take the pointwise image of J. Another important property of elementary embeddings that you should keep in mind if you haven't looked at large cardinals a lot before is that J in general for sets of size bigger than, greater than or equal to kappa, J of the set may not be equal to the pointwise image of J on the set. So this is, I think, a common point of confusion for mathematicians looking at large cardinal embeddings for the first time, because you're so used to writing that J of S to denote the pointwise image of S. But now you have a function that acts both on S and on elements of S. So you have to really keep track of when you mean J of S and when you mean J pointwise image S, which is why you end up with this notation, J square brackets, which is, I mean, maybe it looks pedantic in general, but it's very important to keep track of this. But okay, in this case that we're in, fortunately, the two sets coincide. And so J of sigma is contained in the range of J. And J image gamma, as I was just saying, it's in HOD as computed in M. Okay, but finally, the cardinality of J image gamma in M, well, the cardinality is just gamma, right? Because there's a bijection between gamma and J image gamma in M. It's just J itself, because M is closed under delta sequences, it can see. And gamma is less than delta, which is less than J kappa, right? Because of how we select the elementary embedding. So kappa is mapping up above delta. In particular, it's going above gamma. So we found our set. Have that J of sigma is contained in this M ordinal definable set, which has small cardinality in M. Okay, so that completes the proof. So what we did, just to summarize, is we took some sigma containing gamma, small cardinality, and instead of showing in V that we could cover it by an ordinal definable set, we moved sigma into this submodel M and showed that we could cover J of sigma there. And that used the fact that we could define this J image gamma set, which served as the cover, using the image of the stationary partition. But the stationary partition we could assume was already definable. And that's because we were in this side of the HOD dichotomy where delta could be partitioned into at least gamma many stationary sets. So that's how this proof works. So you have one of the following two statements. Either you have this covering property. So you can cover sets of size smaller than kappa with ordinal definable sets of size smaller than kappa. Or you have this very strong anti-covering property where you cannot split stationary sets in an ordinal definable way. Okay, so you'll get to sort of complete the proof of the full HOD dichotomy theorem in the homework. And yeah, thanks for listening.
Okay, thanks. Any questions or problem?
Kate?
Yeah.
I wanted to ask you about a remark you made at the very beginning of today, which is when you build L, but you use definability without parameter, still get L. Is there an obvious way to see that? Is there some sort of tricks?
Well, yeah, the trick is just that because you take unions at limit levels, you actually end up building the same thing. I don't know if I can say it better than that. So at the successor stages, you're only going to get countably many sets at every stage. But then you put them all back together at the limit steps, and that gives you the all the constructible sets in the end. I hope that makes, I don't know, that gives you some clue how to prove it. You can do some kind of induction, like you want to, suppose you have collected all the sets in L alpha so far, and you want to show that all the definable from parameter sets are in there, but then you have to show that there's some stage in the L hierarchy where the set is definable from the ordinal parameters. Right? You got to be a little careful, but you can do it.
Okay, I think I got it. The point is you got all the ordinals in limit
Yeah.
stages, and then you could basically read L off those ordinals. That'd be the idea.
Yeah.
All right.
Mm-hmm.
Great. Thank you.
Yeah.
Okay, any more questions? So, okay, that's all for today. Thanks, Gabe, and see you tomorrow. Okay.
Yeah. Bye.